Again, welcome to Jnana Learning. So, continuing with the lecture on digital signal processing, and today we are discussing DFT, that is discrete Fourier transform, and its properties. So, first of all, we have to know the difference between DTFT and DFT. DTFT is a discrete time Fourier transform and DFT is a discrete Fourier transform. Discrete time Fourier transform, you may be learned discrete time Fourier transform or DTFT in lower classes, and it is the conventional Fourier transform of a discrete time signal, and its output is continuous in frequency and it will be periodic. But the discrete Fourier transform, it is somewhat different from that of the DTFT. That is, DFT can be seen as a sampled version, that is in frequency domain, of the DTFT output. That is, DFT, it is the sampled version of DTFT output. Actually, DFT, it is used to calculate the frequency spectrum of a discrete time signal with a computer, because we know that computers can only handle a finite number of values. So, we can say that for a DTFT, the input signal will be discrete and infinite and its output will be continuous and periodic. But for DFT, the input will be discrete and finite and its output will also be discrete and finite. So that's why we can compute the DFT using computer or processors. So that is the basic difference between DTFT and DFT. So DFT, it is a most important tool in digital signal processing. So here we discuss the expression for discrete Fourier transform and inverse discrete Fourier transform. So first, the DFT. So here x of n, that is small x of n, it is the input, and x of k, it is the DFT of x of n. Now the small n, it represents the time domain ordinal, and capital N, it represents the length of the sequence to be transformed, and k, it denotes the frequency domain ordinal. So the DFT x of k is equal to summation n equal to 0 to capital N minus 1 x of n into e raised to minus j 2 pi by capital N into nk, and the value of k is from 0 to capital N minus 1. And the expression for inverse discrete Fourier transform is that small x of n, which is equal to 1 by capital N summation k is equal to 0 to n minus 1 x of k into e raised to j 2 pi by capital N into nk, where the value of n is from 0, 1 to capital N minus 1. So we can find the IDFT from the DFT of a particular signal. That is, we can find the DFT for x of n, and from that we can find out the IDFT from x of k. And in DFT, the value of k will be from 0 to capital N minus 1, and in the same way in IDFT, the value of small n will be from 0 to capital N minus 1, where capital N is the length of the sequence to be transformed in case of DFT, and in case of IDFT, capital N, it is the length of the sequence that is being transformed. So that's the DFT and IDFT. In DFT and IDFT, there is a factor known as twiddle factor, and it will be very helpful while doing the fast Fourier transform and all that we will discuss later. So we know that the expression for DFT, that is x of k is equal to summation n equal to 0 to n minus 1 x of n e raised to minus j 2 pi by n into nk, and this particular factor is known as twiddle factor, that is e raised to minus j 2 pi by n. this particular factor, which is represented as W of n, it is known as the twiddle factor. So we can write that x of k is equal to summation n is equal to 0 to n minus 1 x of n into Wn raised to nk. So this is the twiddle factor, and its importance is in doing the fast Fourier transform and all that we will discuss later. So next we discuss the various properties of discrete Fourier transform. So similar to that of Z transform and other transforms, DFT also have many properties. So we will discuss one by one. Let x of n be the finite duration sequence and x of k be the DFT of x of n, that is x of n in time domain and x of k in frequency domain. So first property is periodicity. That is, if x of n is equal to some x of n plus capital N, where capital N represent the length of the sequence, that is, we are adding that capital N to N, then in frequency domain we have x of k is equal to x of k plus that same capital N. That is, the same periodicity will be maintained in time domain and frequency domain. The second property is linearity. So suppose that x1 of n and x2 of n are two finite duration sequences, then a1 x1 of n plus a2 x2 of n will have a transform in frequency domain as a1 x1 of k plus a2 x2 of k. That is a linearity property. Then the third property, that is time reversal. That is, if we are reversing the time by capital N, that is, if the signal in time domain is x of capital N minus n, then in frequency domain we will have the transform as x of capital N minus k. Next property is circular time shift. That is, we are shifting the signal in time domain by a factor L, that is x of n minus L. Then in frequency domain, its transform will be x of k into e raised to minus j 2 pi kl by capital N. So this particular term will be multiplied with the x of k. And similarly, if we are doing the shift in frequency, that is circular frequency shift, then in time domain we will have x of n into e raised to j 2 pi ln by capital N. That is frequency domain, that shift is represented as capital X of k minus L of n. So there is a shift by a factor small n. Next property is circular convolution. Again consider that x1 of n and x2 of n are two finite duration sequences. Then x1 of n convolution x2 of n, that is x1 of n circular convolution x2 of n, we will have the transform, or in frequency domain we can say that it is equal to x1 of k into x2 of k. That is a convolution, circular convolution in time domain. We can have the products in frequency domain as x1 of k into x2 of k. And the next property is circular correlation. That is, consider x1 of n is a signal and y star of minus n. Then the correlation between x1 of n and y star of minus n. Then in frequency domain we have x of k into y star of k. That is, it is a conjugate. Star represent conjugate. And then next is a multiplication of two sequences. So x1 of n into x2 of n in time domain we have 1 by n x of k circular convolution x2 of k. That is convolution in frequency domain, we have the product as x1 of n and x2 of n in time domain. And the next property is a complex conjugate. That is, let x star of n represent the complex conjugate of x of n. Then in frequency domain we have x star of capital N minus k. And the last property is Parseval's theorem, is based on the Parseval's theorem. That is, it states that summation n equal to 0 to n minus 1 x of n into y star of n. Then in frequency domain we have 1 by n summation k is equal to 0 to n minus 1 x of k into y star of k. So these are the important properties of discrete Fourier transform. So that's about DFT and its properties. So thanks for watching the video. Continue watching the lectures of this digital signal processing. So for more updates, please subscribe our channel Jnana Learning. Thank you.